remote sensing. Let's see what terrestrial remote sensing can tell us about the planets. We're going, whoa, deep end, you know, what is all this? So we did it, okay? We had 3 in that class, and we learned that. We learned remote sensing from the entire electromagnetic spectrum, how to turn that into something that would be useful to look at other planets before you could get there. Now, of course, Tim disappeared from my last year. You know, he's gone. He's to Flagstaff working with Gene Shoemaker on what it's like to go to the moon and wrote a book on lunar stratigraphy. I'm back home trying to figure out what I'm going to do for a career, you know, knowing that there's no fundamental problems left in my field. And yet Tim had instilled in me something that I think is really what his influence is all about. I went to get the college placement annual. You all won't know what that is, but in my day there was a book they put out with jobs in it, okay? I looked in the back, geologist, page 19 through 23, and 52. I said, whoa, there's an outlier. I looked up 52, okay? 52 was pretty much this, a full-page picture of the moon. And it just simply said, our job is to think our way to the moon and back. And I thought to myself, damn, how do you do that? I said, yeah, I'd really like to try that. But I don't know anything about the moon. And it's like, you know, it's like awe and fear again, okay? Wow, I'd really like to try that. But, you know, well, there's a little phone number in the bottom. And I called. It was NASA headquarters. And I went down there for an interview, knowing, well, maybe I'll see something about the moon or something. I got the job, okay? I was scared to death that they would find out that I didn't know anything about the moon. But as we were talking about earlier, you know, nobody knew what they were doing in terms of the moon. There wasn't any data. There wasn't any information. And as Indiana Jones is wont to say, we're making it up as we go along, because that's exactly what we were doing. Tim Much gave me the courage to take that job, to pursue it and take that job. Well, this led to Apollo. It was amazing. I mean, it was my first job out, as Joel mentioned, was working in astronaut training, selecting the landing sites, training the astronauts in geology, working with them when they were on the moon, and then when they came back, analyzing the data. An absolutely phenomenal job, and I'll share with you in a minute or two what we actually learned from that. Tim, of course, by this time, oh, moon, been there, done that. We haven't even landed Apollo 11 yet. He's off working on Viking, okay? That's the visionary. He's way ahead of the game, okay? And I followed that influence in thinking as well, while on the one hand I was doing my job at Apollo. Well, of course, I put my little spacesuit here on, and that's Brown University Bear there, and really kind of worked out into the rest of the solar system throughout my career. And it's been an incredible time for exploration and understanding. And of course, I started as a geologist, so I'm starting right here, okay, on the Earth. What do geologists take to this whole game anyway? It turned out a parallel revolution was going on in Earth science. We were understanding, in fact, from satellites like Sputnik and other things that were looking down on the Earth and control that was being gotten on the total characteristics of the Earth's crust and the shape of the Earth, that indeed the rocks were deformed and modified by global plate tectonic processes. And this was amazing. I mean, it was just a parallel revolution. While we were exploring the moon, we were understanding the Earth. Completely parallel things that came to converge later on. So we had subduction, we had renewal. And the key point here is that during this whole process, the Earth is so active and dynamic that it's actually losing the record of its earliest history. So let's take a look at this then, okay? We have a very active Earth with atmosphere and lithosphere moving around, oceans and erosion. Bottom line is, what is the history of the formative years? What happened in the earliest history of the Earth? This record has been completely wiped out on the Earth. A few little fragments here and there, but for the most part, we simply don't know what the first half of Earth history was like. If you think about this in terms of a clock and start with the origin of the Earth and work your way around to the present, and you say, well, let's see how much of the surface of the Earth remains from these times. 2/3 of the Earth's surface, the ocean basins, are less than 200 million years old. That's about 5% of the history. The rest of it is in bits and pieces and continents, and essentially for the first half, we have almost nothing. So if you want to understand somebody, of course, you need to know their formative years. If you're reading a history book and all you have is the last 2 chapters, you're not going to understand what's going on. You need to understand the formative years. And this was of critical importance to understanding the Earth. We need to find the major processes that were operating in the first half of solar system history. So this was the beginning of comparative planetology. Where is the record of these processes operating in the first half of solar system history? Planets and moons, indeed, were soon to join the Earth as geological objects. Previously, they've been astronomical objects, but now they became geological objects. We were on our way to a grand experiment, field of comparative planetology. Let's erupt a volcano. on the Earth. We know what that looks like. Let's erupt that on the moon, where gravity is 1/6 that of the Earth. Let's erupt it on Venus, where there's a huge atmosphere of pressure, like on the bottom of the seafloor. Let's erupt it on Mars, where there's a little bit of an atmosphere and 1/3 the gravity. So this was a grand experiment. It's almost like you're playing God in terms of like having these things to manipulate and understanding these processes, if you will. And of course, the first stop was the Earth's moon. An incredible contrast. Soviet Union was doing just wonderfully. They had so many firsts in the early years of lunar exploration. It was stunning. For example, 1966, Luna 13, Luna 9, the first soft lander, these were not trivial objects. These were things that we're still working in some ways to try and catch up on in terms of the techniques they use. Does this look a little bit like, you know, some of the Mars landers some 30 years later? It sure does. It's the same design. We never tried it before that. The Soviets did it in 1966. I don't want to seem unpatriotic here, but they were really doing great stuff. It's amazing. And all my years in the Soviet Union have taught me in detail what indeed they're capable of. These are pieces of the spacecraft that landed just before this, and I'll show you in a second how they actually accomplished that sort of thing. Again, Ranger, not doing too well on this, but the last three caught on, so to speak. I mean, how hard is it to lash a camera to the front of a spacecraft and have it hit the moon? Turns out it was pretty hard, but we learned how to do that, and we began to, in fact, exceed the Soviet Union in accomplishments in getting to the moon. But let's take a look at what happened here. Soviet Union, U.S. space race to the moon. USSR, 48 attempts, 21 were successful. You say, oh, bad Soviet technology. Well, yes. I mean, our record, can we say, is just better, okay? But, you know, nothing ventured, nothing gained. A lot of engineering and testing was done on the fly, so to speak, here. And a lot was learned in these early days. Indeed, all of this led to both countries absolutely had human exploration programs for the moon. The Soviets denied it for decades after their N1 failed. But indeed, they were on the road to send humans to the moon. I've talked to some of the cosmonauts. I've seen the equipment that they built for lunar landers and so on, and it's totally real. Well, of course, the early years, they still excelled, okay? This is the Lunicod, an automated lunar rover, 30-some years ago, maybe close to 40. And they also returned samples from the moon with automated spacecraft. Most people don't even know this. We have samples in our lab from the Soviet Luna 16, 20, and 24 missions to the moon. 3-sample return mission. This is how that lander works. Look at this thing here. Looks like a Victorian something or another, but the thing works. It pops off this airbag, bounces around, deflates, comes out, opens this up, rolls over right, and there it is. Okay, that's technology we didn't try for decades in the U.S. part. Well, quickly, of course, this was eclipsed by our successes in Apollo. Apollo 12, we landed next to the Surveyor spacecraft and sampled parts of it. Apollo 15, we drove 7 to 10 kilometers away and sampled things that are just unbelievable and changed our total view. Apollo was completely amazing, and I want to emphasize this just with a few slides of the later missions and the kinds of things that were done, because they completely changed our view of our own home planet and the moon. For example, on Apollo 15, the mission that Dave Scott and Jim Irwin landed on the surface of the moon while Al Worden was in orbit, was an amazing geological mission. It employed the lunar rover, which gave us, 20s of kilometers around the surface, and indeed was able to carry the astronauts down here. You can see the scale here. Here's 4 kilometers, actually 5 kilometers here, all the way down to the base of the mountains out here to the rill, and was instrumental in the success of sampling different geological terrains of different ages. And indeed, a couple of weeks ago, Dave Scott was in our lab, and it's just wonderful to see a young graduate student, maybe 21, 22 years old, showing the commander of the Apollo 15 mission green glass that he'd collected 30-some years before, and getting excited about the fact they had just detected, with new technology, water in the glasses. This has revolutionized our thinking about the moon, with samples were collected that period of time ago, and this is the kind of legacy we have here. We have a legacy from Apollo that we can look into with increasing capabilities of instruments. Apollo 17, the first geologist astronaut on the moon, Harrison Schmitt. This is Gene Cernan driving the rover. Jack also discovered green glass. We found this orange glass at the surface, explored huge boulders on the surface. There's a little rover there compared to this. We knew this was here because it rolled down the hill. We could see the boulder track. We wanted to sample stuff 1,500 meters high. Why go up there when you can take a boulder that's come all the way down? Jack beautifully sampled this area here. And if you can just look in the background here, from here to here, just look at that distance here, that's 2 kilometers. That's end to end the traverses that they went on. Absolutely amazing. Beautiful sampling, unbelievable.